Good afternoon, everyone. My name is Tim Pakulak. I am a co-chair of the Tunneling Association of Canada Young Members Steering Committee, and I'd like to welcome you to today's Tunneling 101 seminar, Intro to Machine Learning with Josephine Morgenroth. So before we get going, just a little bit about TAC-YM. The Young Members Group was created in 2014 as a platform for communication between students, young professionals, and mentors within the industry and other member nations. And we actively create opportunities for young professionals and students to participate in regional technical talks, regional and international webinar series like this one here, field trips and site visits, and conferences and workshops. There are currently 4 active Young Members Groups across the country. So 3 on the East Coast, Toronto, Montreal, and Kingston, and then 1 on the West Coast out in Vancouver. A couple other things to talk about. So there are scholarships and awards available through the Tunneling Association of Canada. And so there are 2 specific awards. There's the undergraduate scholarship valued at 2,000 Canadian dollars and is intended for undergraduate engineers in the fields of geological or civil engineering. And there's also the Dan Eisenstein Scholarship valued at 6,000 Canadian dollars, and it's intended for postgraduate students planning to undertake or currently undertaking postgraduate studies in the field of tunneling at a recognized Canadian university. Fun fact, our speaker, Josephine, is a former recipient of the Dan Eisenstein Memorial Scholarship. And if you would like to join the ranks of fantastic people like Josephine, applications are due May 19th, 2023, and can be found at the QR code shown on the screen in front of you. Some other exciting news. TAC is hosting their annual conference this year, so it'll be September 24th to 26th, 2023, held in Toronto at the Westin Hotel on the Harbourfront, and abstracts are due tomorrow, so that is April 21st, and you can find the conference website at tac2023.ca or use the QR code on screen. And then other exciting news. So the Tunneling Association of Canada has submitted to the International Tunneling Association its proposal to host WTC 2026. If you would like to read the proposal, use the QR code on this screen. It will take you to the executive summary available both in English and French, and our actual proposal that we've submitted to the ITA. Encourage your friends, encourage your colleagues around the globe to vote for Canada. So the vote will be taking place in Athens this May at the World Tunneling Congress there. And if all this sounds exciting to you and you would like to get involved with either the Tunneling Association of Canada Young Members on our steering committee or behind the scenes, you can reach out to us at Tunnel Canada on Facebook, at TAC_young_members on Instagram, or send us an email at tac-ym@tunnelcanada.ca. And so without further ado, I would like to introduce our speaker. So Josephine is the Technical Services Manager at Rockmass Technologies in Toronto, Canada. She has 9 years experience in consulting for mining and tunneling projects, most recently working on the Ashbridges Bay Treatment Plant Outfall project in Toronto. In 2022, she completed a PhD on the topic of practical applications of machine learning to underground rock engineering. Josephine combines her industry experience and research expertise at Rockmass to develop new digital mapping technologies and strongly believes in leveraging digital tools to improve engineering decision-making. She is passionate about EDI initiatives and empowering underrepresented groups in STEM through intentional action. And so, Josie, I would like to pass the floor over to you.
Great, thanks. If you could just confirm that you can see my screen, we'll get things going here. Is that a yes? Okay, I'm going to assume you can see it. Thanks everyone for joining today. I'm really excited to be talking to you about this topic. As Tim mentioned, I recently completed my PhD research on machine learning in rock engineering, which is my primary background. And I'm really passionate about the use of data, efficient use of data, and how we can improve engineering decision making. And it's my opinion that machine learning is one of the tools that we can put into our engineering toolbox. And not that we all have to be experts, but if we can at least understand it, then I think we can leverage the opportunities that it presents. So I'm hoping today we'll give a little bit of an overview of what machine learning is and how you might be able to use it, and a little bit of a shameless plug, but some of the work you'll see today will be presented also, pending abstract acceptance at the TAC conference, which is happening in October. So I hope you can attend. So first and foremost, I'd like to get a little bit of an idea of who we have in the audience today. So I'm hoping you have access to these little reaction buttons at the top of your screen. And if you have heard of machine learning, but don't really know much more than the word and hoping to learn more today, if you could give this a thumbs up, that would be really helpful for me to know who we've got. And if you have dabbled with things like ChatGPT or Lambda or any of those natural processing programs that have been on the scene and are really popular these days, give it a heart. Great. And finally, if you've written any ML code yourself in whatever language of your preference, give some applause. You should be patting yourselves on the back, giving yourself some applause. So yeah, if you could go ahead and do that. Okay, great. Looks like we have a good mix today. So I'll try to tailor the conversation to that. So first and foremost, I want to make sure that we're all on the same page with respect to the terminology and the nomenclature. And something I get asked a lot is, are AI and machine learning the same? And the answer is kind of yes and no. As with most things in our industry, it depends. But really, machine learning is a subset of AI. And I'm going to demonstrate here with a little diagram. So if we look at the entire field of AI or artificial intelligence, this is any technique that allows a machine, or in this case, a computer, to mimic human intelligence. So this could be with logic, if-then statements, decision trees, and yes, machine learning. So any of those types of activities are all considered AI. Within that, we have the field of machine learning. So this is a subset. It uses statistical techniques in order to learn patterns in data and therefore learn with experience. And this is called training. I'll give a more specific example in a little bit. So basically, machine learning is anytime you give a program a set of data to learn from. Within that, we have what are called neural networks, and these are a subset further of machine learning, the type of algorithm, and they process data using artificial neurons. You can think of this similar to the neurons in your brain that learn what are called neural pathways to learn those connections and patterns in the data. And then finally, we have deep learning. So this is a multi-layered neural network that has many, many layers of depth to it, and also requires vast amounts of data. And those processing platforms that I mentioned before, ChatGPT, Lambda, et cetera, those are deep learning. But today we're going to stay kind of in the realm of neural networks. So why machine learning? Why is this a powerful tool, and why do I think that everybody should at least be able to understand the mechanics of it at a high level? Well, first of all, machine learning is really efficient at learning nuanced patterns. So traditional ML, as I mentioned, learns from the data that you give it. This is really powerful because it means that we can give ML site-specific data, and then it can learn the patterns and interrelationships and correlations from that. This is actually better than doing it manually. A lot of us have probably spent many, many hours crunching spreadsheets, trying to establish what parameters to use for modeling or what parameters to use for design. But ML is better than we are at this because they can handle multidimensional relationships. Humans can kind of think up to 4D, I would argue more like up to 3D, but machine learning can deal with several dimensions beyond that. And using machine learning actually frees us up to make decisions about what inputs are relevant to what we're trying to predict, and also interpreting the results, as opposed to doing that tedious data manipulation that I was just talking about. So here's kind of a taxonomy of machine learning. I won't get into too much of the end members of this diagram, but I wanted to give kind of an overall frame of reference. So we have machine learning as the kind of overarching theme, and we have 3 different types of learning that I was mentioning before, where we can train an algorithm to learn the patterns. The first one is supervised learning, and I'll talk a bit more about this because we're going to stay in this realm today, specifically within image classification. We also have unsupervised learning and reinforcement learning. So where is machine learning in our daily lives? Some of these examples will seem very obvious to you, but some might be a bit of a surprise. And I want to point out that all the examples I'm about to talk about are commercial examples. None of this is research. These are applications where machine learning is already used and relied upon to make decisions. So of course, we all talk about the algorithm that decides what Netflix show we're going to watch next or who we should request to be friends with on Facebook or Instagram. It's also used heavily in fraud prevention. So if anyone's had the annoying occasion where they've been abroad and suddenly their credit card gets blocked, it's probably a machine learning algorithm that decided there's no possible way you could be on vacation right now and put a hold on your credit card. Part of the theme of today is that machine learning is not infallible, but it is used extensively in fraud prevention. It also helps with commute predictions. So if you've ever been en route and noticed that your route suddenly jumped up by 10 minutes or something like that, it's because there's an algorithm in the background that's trying to predict based on other people and their movements, how fast you're going to get to where you're going. One that's really interesting to me is medical diagnoses. So as I mentioned, we're going to stay in the realm of image classification today, and the medical field is actually one of the leading drivers of this type of machine learning. For example, if they're doing CAT scans or any sort of medical imaging, machine learning algorithms have been developed to kind of identify malignant or problematic areas in those scans well in advance of what a doctor could do with their naked eye. And that's not to say that the machine learning algorithm is diagnosing you, but what it is drawing attention so a trained professional like a doctor can look at that and then make a decision whether a diagnosis is necessary. We also have an example of flood forecasting. So one of my co-supervisors for my PhD actually specializes in this. I know the city of Calgary and the city of Toronto both have very rigorous flood forecasting systems that rely on machine learning algorithms. These take in data such as the rainfall, topography, river levels, all these types of hydrological parameters in order to predict whether there's going to be a flood downstream and to trigger an early warning system. We also have a really interesting example with pollution tracking. This is a project by IBM where they're actually tracking pollution. I believe it's in China, I want to say in Beijing, where they track the pollution and predict where the plumes of pollution are going to be spreading given certain weather patterns and climatic changes. And finally, supply chain planning. So this is, I think, evolved quite a bit because of the COVID-19 pandemic, but machine learning can kind of predict whether any disruptions in these supply chains are going to cause issues downstream. So I did put in the title, these are all examples that make the world a better place, because of course we've all probably watched those documentaries or heard about how machine learning can also maybe make the world a worse place, but we're going to try and stay positive today. All right, so now you've decided, let's pretend that I've convinced you that machine learning is a good technique to use in tunneling. So how do I start using it? The first thing is to choose a programming language. I understand that as engineers, especially a lot of us with geotechnical or civil infrastructure backgrounds, coding is kind of a realm that we don't dabble with too much beyond using the program someone else has developed. But I'm here to tell you that if I can learn how to code, so can you. And there's lots of free ways to get started, lots of online resources. Python is one language that's not only free to use, it's also the gold standard for machine learning. There's lots of packages and lots of libraries that exist out there that you can use for free. And also there's lots of communities that you can access in order to learn how to write your own machine learning algorithms. I linked one here. You'll see these QR codes throughout my presentation to resources that I think might be helpful in this topic. This is a course on using machine learning in Python that one of the software developers at RockMaths Technologies actually recommended. So I wouldn't put here if it wasn't vetted. Another language that you can choose to use is R. Again, it's free, it's easy to learn. I'm told I don't write in R, but some people learn it in school and so therefore are comfortable with it. Again, lots of free resources because it's used very extensively in research. And finally, MATLAB, unfortunately not free, but lots of companies already have licenses, so maybe you can piggyback off of that to dabble around. MATLAB is what I use because it's what I learned in school. it's also very easy to get started because there's a GUI that's built into MATLAB specifically for new users of machine learning. So it will have a dialog box where you can put your inputs in and your outputs and adjust some of the parameters. And it's a little bit more intuitive than trying to write all the code. That GUI also lets you export the code so that you can start to make some changes as you get more comfortable. So yeah, there's lots of free ways to start with machine learning, specifically with Python and R. But MATLAB is what I'll be talking about today because that's what I write my code in. All right, so you've decided to use machine learning, you've got your environment set up, you know where you're going to code, and now where do I start? What kind of algorithm am I going to use? Well, there's a few questions you have to ask yourself first. This is analogous to doing any sort of numerical modeling. You don't just start by throwing all the spaghetti at the wall and see what sticks. You want to start simple, work your way up, and be very conscious about the decisions that you make along the way. So the first thing you should ask yourself is, what kind of input data do I have? What is the quality, quantity, and sparsity? So this is something that's really important in machine learning because any pattern that you give the algorithm to learn is what it's going to put out. So you want to have a good idea of your inputs, if they're categorical or numerical, if there's holes in your data, if there's interpolations that were done by, let's say, a third party, like I'm thinking of microseismic arrays that are outputting parameters that they're not directly measuring, for example, and so on. So you want to have a really good understanding of what the data quality is that you're dealing with. Of course, quantity. For machine learning, general rule is the more data you have, the better. There are techniques to deal with less sparse or more sparse data, less quantity of data, but I won't talk about that today because it's a little bit in the weeds. If you're interested, you can contact me after the presentation. The next thing you want to ask yourself is, what am I trying to predict? Am I trying to predict a category, like a class? So for example, a ground class, or whether the liner is going to fail or not fail, so a binary class, or am I trying to predict something that's continuous, so numerical, stress level, or amount of groundwater inflow, or amount of subsidence? These are all examples of things that have actually been done in the tunneling world. So you would choose your algorithm based on that. And like I said, like with any type of modeling, you want to start simple and increase complexity. So maybe use less inputs for only one output, or use a more simple algorithm type to get a simpler output before you build up the complexity. I think Mark Diedrich coined this phrase as far as I know, but garbage in is garbage out. So you want to make sure that you're starting not with garbage. So this chart is something that I developed as part of my early days of PhD research when I was still learning about the different algorithm types and what they do. There's a QR code there on the right. It's free to read. But basically, this chart is more of a qualitative chart, and it'll show you on the x-axis, the redundancy in the data. So how many examples of the phenomenon that you're trying to predict you need to have in your data set versus the amount of data on the y-axis. So whether it's really sparse or whether you have a really rich data set. And these three items that I have here already in red, those are not algorithms. Those are engineering tools that we already use. So deterministic methods or regression methods require comparatively less data and less redundancy, because it's for deterministic, it's, for example, just y equals mx plus b, or regression is just a curve fitting function. For something like a probabilistic analysis, you'll want likely more data, not necessarily more redundancy, but more data. And now if we start looking at the algorithms, there's one called k-nearest neighbors. So what happens here is the value that you're trying to predict. The algorithm will search the nearest neighbors. In this case, k is 3 because it's looking at the 3 nearest neighbors, and it'll make a prediction based on that. So this is really good for spatial data that has geospatial dependency, which we're often dealing with in our industry. Now, let's say you don't know what the output is. You just want to know if there's any patterns in the geospatial data that you have. Then you can use an algorithm type called clustering. So these are two different types of clustering algorithms. But basically, it'll look for commonalities between the inputs and then give you groups. So you can decide this group is X, this group is Y. It won't tell you what the label should be, but it will tell you these data points have something in common. Next, we have something that is also pretty familiar on a smaller scale to us, which are decision trees. And there is a machine learning algorithm type called random forests. I think it's aptly named, a forest is many trees, and that's exactly what this algorithm is. There's many trees that are run in parallel that each try to make a classification, and then in the end, it'll take a weighted average of what the classification is and tell you what the most likely class is for the input data that you've provided. We also have statistical-based machine learning algorithms that are based on Bayesian statistics. So Bayesian statistics uses a prior level of knowledge. It has a prediction that what it thinks the answer is going to be based on that prior knowledge, and then it updates that prediction based on new information. And finally, the star of today's show, artificial neural networks. Artificial neural networks are consisted of nodes of input data that are connected through many, many connections through, in this schematic, one output, but it can be multiple outputs. And these require a lot of data and a lot of redundancy, but are really, really good at identifying those patterns. So I've mentioned before the term training of an algorithm. So it's the same way, I think, as training a puppy with lots of repetition. There's lots of different ways to do it. But at a very basic level, machine learning is trained based on examples between the inputs and the targets, if applicable. And what I say by that is, as I mentioned a few slides ago, there's 3 different ways to train an algorithm. The first one is the most obvious, which is called supervised training. This is where you have a set of input parameters and you know what the corresponding output is. And now you want to train the algorithm to be able to reproduce this connection. So that's called supervised. There's an unsupervised method of training. This is where you don't know what the output is, but you have a bunch of inputs that you know are correlated. So this is similar to that clustering algorithm I was talking about earlier. You train the algorithm with a bunch of unsupervised input data points, and it'll tell you what the output groups should be. And finally, we have a relatively new method of training on the scene, which is called reinforcement training. This is where the ML gets a reward when it finds appropriate targets and also gets punishments when it doesn't find appropriate targets. This is very interesting to me, but I won't talk about it too much because it is relatively new and I don't want to put my foot in my mouth. But I'm going to focus on the supervised method of training an algorithm. So this is a schematic of a very simple artificial neural network, again, the star of today's show. On the left side, we have a layer of inputs. So here there are 4 inputs. This could be geology, geometry, groundwater inflow, stress, whatever it is, whatever's relevant. And then you have your output, a prediction, which could be liner deformation, for example. If it's continuous, if it's a numerical output, it could be amount of deformation. If it's categorical, it could be class of deformation. In between, we have what's called the hidden layer. The hidden layer is where all of the connections and the beautiful math that I won't bore you with happens by applying what's called a weight and a bias to the inputs and all the connections. So I've got a little animation here. Basically, this data gets fed forward through this network. The output gets compared to the ground truth. This is the target that you've provided, your data set, the answers you've provided. And once that error reaches an acceptable minimum, then the algorithm is trained. And now you have a network that's basically like a custom-made equation that you can give new data to, and it should make a new prediction. But the question is, how do we know the training is good? And I'll tell you how we know the training was good. My slides will advance. There we go. Okay, so training and overfitting. So I'm going to show you another graph here, and sorry, I wanted to recreate this, but this is one I pulled from the internet. You can look at the original source if you want. But basically, the X and Y axes are the weights and biases that I mentioned in the hidden layer. And what's happening during the training function is that we get a point that gets dropped somewhere on this surface. This is a solution surface. And what happens during that successive feed forward and back propagation is that the network is searching inside this grid for what is called the global minimum. And this is where the error is the lowest. The algorithm does not know whether it's fallen into a local minimum or if it has found the global minimum. And that's up to our interpretation of the outputs to be able to know. So basically what we're looking for, you can look at these little charts here at the bottom. We don't want that our algorithm is underfit, which means that it just doesn't reproduce the phenomenon that we're trying to predict. but also we don't want the algorithm to be overfit, meaning that it can produce exactly the input data, but if I throw something new at it, it won't be able to make an accurate prediction. So of course, just like Goldilocks, we want something that's just right, somewhere in the middle. We want an algorithm that is, like I said, essentially a custom-made function or empirical solution, but it's a machine learning algorithm that can reproduce most of the data points, but doesn't reproduce them exactly, because if we reproduce them exactly, it means that it's not well generalized. We want a well generalized solution because it can handle new data well. So one way we can make sure that a solution is well generalized is by using a technique called ensemble modeling. And this basically means that we can run multiple machine learning algorithms in parallel, train them all randomly, initialize this starting point randomly at different places, and then compare and get a statistical distribution of what the possible predictions will be. So if I could use a rock mechanics analogy, we're usually dealing with, let's say, one slide model or one FLAC 3D model that gives us a deterministic value of what the stress state is going to be, for example. Machine learning will give us 100 different possibilities of what the stress state will be, and therefore a statistical distribution. So we can have increased confidence with the prediction that our model is making. I think this is one of the great opportunities with machine learning, because they can actually be used hand in hand with numerical tools in order to constrain our decisions a little bit better. So one way to do this ensemble modeling is actually to take your training data set. So this is the whole data set, this continuum, and we take part of the data set and we say, okay, we're going to train the algorithm using only this part of the data set. And then we're going to give it the validation portion of the data set, which is another part that we've reserved. Once it performs well on the validation data set, then we've considered the algorithm trained. And finally, we will test it on data that we've kept apart from the algorithm the entire time. So we'll do this. In this case, this is called five-fold validation, but we could do this 100 times, where the algorithm is given different training and validation subsets throughout the training process, and then tested on the same subset that's been withheld the entire time. So now I want to talk about machine learning in a real tunnel project. So this is actually from a project here in Toronto that I collected data from recently. We've submitted an abstract to the TAC conference. So what you're about to see is a work in progress. And hopefully if you can attend the TAC conference in October, you'll see the final product. I should have mentioned at the beginning, I'm really sorry, but I can't see the Q&A while I'm presenting. So just make sure you're writing down any questions you have there, and I'll make sure to answer them at the end of the presentation. So this tunnel project, to give you some background, it's a PCTL lined tunnel, 7 meters in diameter in downtown Toronto. And unfortunately, we started to notice that there are some cracks and some buckling in the tunnel crown. And we want to make sure that we're monitoring these continuously during construction so that we can advise our contractor when and whether to repair them. It's not whether, but when to repair them, and also to track if they're getting bigger. So what we did is we use, this is the DXF file of the annotations that we did. So what we did is we went underground, myself and Eliane Cabot, shout out to Eliane because I think she's here today. We went underground with the RockMass solution, the mapper, and took some LiDAR imagery of the tunnel segments in order to identify where these cracks were happening and to extract real LiDAR point clouds. So 3D data, 3D images essentially of these cracks. If you're interested in this, I have some contact information for you at the end. So now we wanted to train an algorithm in order to predict where these cracks were. So like I said before, we want to start simple, increase complexity. So the simplest thing to do first is to be able to train an algorithm to say, is this a crack or is this not a crack? So we took that LiDAR data that we captured. This is the LiDAR point cloud. I flattened it. So this is now a 2-dimensional image, and it has 3 channels, red, green, blue. So this is very typical for an image input into a machine learning algorithm that you separated into its channels. I didn't tell it the answer at this stage. This is just the input, and each value in each cell has a red, green, blue value. And then we have the target data. So here it's very simple. I hope that you can see that, but that red line is just that DXF file from the annotation I showed in the previous slide. And that was turned into a raster that's just binary values. Either black is 1, white is 0, meaning black is there's a crack, white there's no crack. So this is the data. This is it. This is the only thing I used to train this algorithm. So what kind of algorithm did I use? So I used a type of artificial neural network called the convolutional neural network, which is a really powerful image processing algorithm. And that's because it can process both spatial and temporal relationships. So if you've ever seen kind of image prediction or like computer vision, those are really advanced convolutional neural networks. Something that, for example, autonomous driving relies very heavily on. So how does this algorithm work? First, we have the input layer. So the input layer is consisting just of this image, which has red, green, blue channels. And then we apply a convolution layer. The convolution layer uses a filter, which is basically a search area that strides over each successive selection of cells in order to see if there's anything quote unquote important for it to extract. So a relationship between the red, green, blue channels that are a strong indication of what the output is, which is the crack or not crack. And what it does is it extracts these feature maps, which are basically a little spatial representation of those important features. Then we have the activation and deconvolution. I won't get into too much detail here, but basically the activation function decides whether or not that feature is important. And then the deconvolution layer does the opposite of this step, where it upsamples these feature maps back into an image that's the same dimension as the input image. At that point, each pixel will get classified either a crack or not a crack, and the output will be the same dimension as the input. So you can see, similar to the schematic I showed before, which was a bit simpler, we have an input layer, we have an output layer, we have a bunch of layers in between, and what happens during the training process is there's a feed forward of information, then there's a comparison to the output crack, and then there's an error calculated, and that error gets back propagated until we've reached the minimum threshold, and then the algorithm is trained. So I want to show you some performance. I apologize in advance for the code. Don't worry, you don't have to read it. I just want to point out some important metrics. I didn't have time to make this look too pretty, unfortunately, but this is the output. Once you've trained an algorithm, it gives you a bunch of metrics so that you can see how well your algorithm did. First, we'll look at the global accuracy. Wow, like 99.8%. That's really good. That we only have 2 classes. So if it's 99.8% accurate, that's amazing. But then we look at the mean accuracy, and it's 49.9, so basically 50% accurate. That's not really all that good. We only have 2 classes, crack or not crack, which means it must be doing very poorly at one of those 2. And sure enough, it's really good at recognizing where there's no crack. So 99.95% accuracy, that's great, except we don't really care if there's no crack. We only care if there is a crack, and it's 0% accurate at doing that. So this is not very well trained. This is the first pass of training the algorithm. But another way to visualize this performance is through what's called a confusion matrix. So I did make that a little bit prettier here. Confusion matrix is a way of telling whether a classification algorithm is getting confused during the performance, during prediction. So I used to think it was my confusion, but no, it's the confusion of the algorithm. So on the y-axis, you've got what the algorithm predicted, and then on the x-axis, you have the true class. So we want our on-diagonal values to be as high as possible, because that represents how often the actual class was not crack and how often the algorithm predicted, yes, there is a crack. So that's 862,000 times it was correct. But there were 0 times where there was a crack and it predicted there was a crack. So that's 0% accuracy. That's not very good. Okay, so what are we going to do about this? There's a few things. I love this cartoon my sister made of me, but I'm going to replace the rock with an artificial neural network for the purposes of this presentation. So we're going to look a little more closely at this network. This was just one model, so not an ensemble like I mentioned before, and I haven't done any fine tuning to any of those parameters in between the input and the output. I just, like the schematic I showed you before, the 5 very simple layers, that's what I ran just one time. So there's lots of things I can do to improve this. All is not lost. The first thing I can do is introduce what's called error weighting. So this allows me to incentivize the machine learning to prioritize learning where there are cracks over learning where there are not cracks, because that's what we care about. And that's something that's, I think, very powerful that we can leverage for engineering applications is, yeah, we may have a bunch of categories that we want as an output, but we can tell the algorithm which ones we care about the most. So when do we want to intervene? When the liner deformation reaches a certain threshold, or when the groundwater flow peaks at a certain flow, or when the slope movement reaches a certain velocity, etc. So we can prioritize what we want the machine learning to learn. The other thing is we can balance the data. So as you might have noticed with those rasters I showed at the beginning, we have lots of pixels of RGB data, but we only have a very few pixels where there are actual cracks. So we can balance this by artificially inflating the number of samples we have where there are cracks and underplaying the amount of samples where there are no cracks. So that, again, this is another way of basically biasing the machine learning to learn where those cracks are. And finally, another technique is called sampling with replacement. So that 5-fold validation that I showed you before, in that example, the training and validation sets are static, but what you can do instead is randomly choose different data points in the set to be training and validation, and that gives you a little more spatial variability in the training and usually increases performance. And finally, as I mentioned, this was just one model, so we need to run an ensemble of models to really get an understanding of what the variability actually is in those predictions. So, I mean, even if I run 100 models, I guarantee you the performance is going to be about 50%, and that's still not good enough. So I'm still going to have to do the other things. Luckily, yesterday I did have enough time to do some of this error weighting, and what I did was I told the algorithm, I want you to prioritize the crack to 100, like finding cracks to 100%, and I want you to deprioritize finding where there are not cracks to 1%. So 100% versus 1%. And now you can see our performance has improved drastically. So now the performance for identifying cracks is 71%, but the performance for identifying cracks is 87%. So it's already a lot better. I think there's still some room for improvement, but this is already very promising. In the research realm, I think I would say I'm happy with the training here. And now what I'm going to do is test this algorithm on another location in the tunnel to see if it's well generalized. But I guess you're going to have to attend my talk at TAC to find out if that's what I did. I just briefly want to give some other examples of machine learning, both in commercial use and in research in the tunneling realm from around the world. The first one is a project based out of Italy. There's a company called ETS. They developed a system that's rail mounted for their masonry tunnels in order to identify defects in the liner. So they have much older tunnels than we do there, but many, many more tunnels as well. So you need to be inspecting them with regular frequency and not be spending too much time doing so, because they have to close the rail line when they do that. So what they came up with is this kind of cart you can see on the right. It's, like I said, rail mounted. It has a bunch of different sensors, LiDAR, high definition cameras, etc. And they've trained an algorithm in order to kind of what we did with the crack and not crack, but identify whether there's water defect or no water defect. And they've got an accuracy of up to 93%, which is really, really great. And this is a commercial product that is used by the Italian National Rail Line. I'll give you the reference at the end if you want to learn more about this. On the research side, there's lots of work being done actually for TBM automation. TBMs are a machine learning algorithm person's dream, because the data that's collected is regular, it's continuous, and it's collected digitally. So you can train an algorithm really well. There's lots of work being done to develop self-driving TBMs. There's some work being done as well to classify geology ahead of the advancing phase, using TBM data to predict when cutters need to be exchanged, etc. And this is really exciting. And I think this is kind of the first frontier of machine learning and tunneling because, like I said, the data is really readily available. So here are some references. I think this will be made available so you can check out the resources I used to put this presentation together. And with that, I will take the questions. If you're interested in getting in touch and learning more about this, you can add me on LinkedIn. If you want to learn more about RockMass Technologies, the company that I work for, you can also scan this QR code on the right. It'll take you to our website. We work upstream of the machine learning side of things on the digital data collection, but we're expanding into machine learning and are very excited about that. So I will ask Tim if he could please read out any questions that came in through the chat.
Yes. Well, thank you for your presentation, Josie. That was fantastic. And I feel that I've learned so much from this. And there are a couple questions in the chat. So the first one that I have here, are your errors based on the training set or a test set? So in theory, the test set is more reflective of model performance, but you have to ensure there are both cracks and non-cracks in the test set.
That's right. Yeah. So I didn't talk too much about data splitting, but there are a few different best practices when it comes to splitting up your data. In this case, it's a spatial problem. So yes, you want to make sure that when you're splitting up your testing and your training set, that there's about equal representation of the phenomenon you're trying to predict in both. In my case, I randomly split the training and test set because it's actually kind of convenient. That image I showed of the raster of the RGB, the crack is kind of continuous across that entire area. So it doesn't really matter which slice of the tunnel I take, there is going to be a crack in it. So in this case, it worked out really well. But if you have kind of really concentrated defects that you're trying to predict, you definitely want to make sure that you're strategic with how you split up the training and testing.
Okay. Fantastic. So the next question that I have here is, I know it wasn't talked about a lot, but how can you see machine learning techniques like PCA or autoencoders being used for data pre-processing?
That's a great question. On the pre-processing side, it is a bit, I want to say, contentious. They're especially in the literature, lots of fields that use geospatial data and natural data like we do, like ground conditions, are very against, artificial balancing or kind of too much pre-processing of the data because of the worry that we're obscuring some of the nuanced behavior that we will experience at our sites. In terms of my opinion, I think just like with any other machine learning techniques, it's good to validate those techniques in comparison to what's done in standard practice and what's best engineering practice before running with it to see if you get a similar result. I have not used pre-processing techniques like that myself because I was able to get good enough performance without overly pre-processing the data before writing an algorithm.
Okay, fantastic. What is the best approach for dealing with outliers? Can we train the machine to recognize them?
Absolutely. I love that question. So I don't think in machine learning, in input data, there is no such thing as outliers. All the data that you have captured that is real to the site that you're working with is real data. So I know that in deterministic analyses, we're really tempted to say, well, that's an outlier. That was just a rogue test value. Especially with lab test data. But if it is really an outlier, then the machine learning algorithm won't emphasize it. It won't learn it. So if there's only a few examples and it's really just erroneous data, the algorithm will determine that there are not strong enough connections between that and the output to include it heavily in the final trained algorithm. However, if there's a nuanced pattern there that we might think is an outlier, but mathematically speaking, the machine learning algorithm determines does have a strong signature, it'll learn it. So I think that's also a really great opportunity. And there's quite a bit, I didn't include it here, but there's quite a bit of research being done on predicting parameters from lab test data using machine learning algorithms that addresses exactly this.
Very cool. That's very cool stuff. I guess like the question that everybody has on their minds is, so as machine learning and these techniques get better, how much longer are we going to be in the tunnels for? Like, are we going to be able to see the surface soon? Can we send a drone to just like fly the tunnel? Like we have the TBMs that collect all their data. Can we put it all together and be done? And like we get to see the sun, or are we still gonna be down there?
I think if you want to be outside all the time, you're in the wrong industry. If you want to be, we're all meant to be underground. We're all here for a reason. But I think that's an interesting question, because I get asked all the time in my capacity as an employee of RockMass if machine learning is going to take your job. And the answer to that is a resounding no, in my opinion, because in the end, the machine learning algorithm is not an engineer. It can't sign or stamp anything, and you're going to be responsible for the decisions that you make based on its outcomes. Yes, there's tons of opportunity to improve safety and efficiency by using tools like machine learning, drone-mounted LiDAR applications, etc. But I think we're a ways away from not having to go underground at all. Okay, which might be good or bad news depending who you are.
If we all want to be in the tunnels, so hopefully like we can stay there. But with that, I don't see any more questions in the chat. So if anybody has any more questions that they think of, just feel free to either send TAC an email, so tac-ym@tunnelcanada.ca, or feel free to reach out to Josie personally through LinkedIn. So. Great. And then thanks for swapping the slide there. So just one more announcement. So again, I'd just like to remind everybody about the scholarships that are available, both the Dan Eisenstein and the undergraduate scholarship. So these are supporting our next generation of tunnelers and tunnel engineers. So please visit the website, so tunnelcanada.ca, under awards. There's a separate application for the undergraduate award and for the Dan Eisenstein. So if you know an undergraduate student, if you know a graduate student, please encourage them to apply. We'd love to get lots of applications in, and we'd love to hand out lots of money. So with that, I'd like to thank everybody for attending. Thanks for joining. Keep an eye out on your emails and on social media for details about our next webinar.
Thanks, everyone.